Hello, this is Mr. Wynn with lesson 10-4, Infinite Geometric Series. Before we start, here's a quick question. If your opponent is on the 10-yard line and the defense is penalized half the distance to the goal, that places the ball on the 5-yard line. If they get penalized again, half distance to the goal, that puts on 2.5-yard line, and then penalized again, put a 1.25, penalized again, it's 0.6 yards off the line, penalized again, puts 0.3, and so on and so forth. If they keep getting penalized, how many total penalty yards will the defense have incurred? This question can be answered by looking at infinite geometric series. So an infinite geometric series has an infinite number of terms. A series as a sum is a convergent series because the sum converges to a specific value. A series that does not have a sum is a divergent series. So when we found the sum SN of an infinite geometric series, the first n terms, we were finding a partial sum. It is possible to find the sum of an entire series. In the application above the following, it seems that the ball will eventually reach the goal line. In the defense, will be penalized a total of 10 yards. The value is actually the sum of the infinite series, 5 plus 2.5 plus 1.25 plus 0.625 and so on. The graph is shown on the left. As n increases, you get really close to 10. Up here would be the 10 mark. Alright, so they will get penalized a full 10 yards if they keep getting halved. Alright, the big thing is it all depends on R, the common ratio. Alright, the series is convergent if R, absolute value R is less than 1. So it's basically between -1 and +1, but it does not include 1 itself. Divergent means the sum will not have a value. That's when R is greater than or equal to 1. It doesn't matter if it's positive or negative because it's absolute value. Here's this example. The number's just getting bigger and bigger. There's no way it's going to add to a number. What happens is this eventually flattens out where the number is constant, where we know exactly what the number is. It's going to be predictable, and it'll cancel out to 0 pretty much. Alright. So, first example, determine whether each infinite geometric series is convergent or divergent. Again, all we gotta do is find R. So to find R, we do the second term divided by the first term. I can divide it by 18 each, so that's 2 over 3. Because R equals 2 over 3, that is less than 1. So R less than 1 means convergent. Just like in that example of the football story is 1/2. Right down here, I tried this. So the second term divided by the first term, I can reduce that, divide by 4 on top and bottom, 3 over 2. Alright, because R equals 3, which that's more than 1. R greater than 1, that means divergent. That means we don't know, we're just going to keep going further and further, infinitely bigger. Alright. So while absolute value R is less than 1, the value of Rn will approach 0 as n increases. Therefore, the partial sums will approach this when you plug in. And here's our brand new formula for infinite geometric infinite series. Again, right here, the key concept, the sum of an infinite geometric series with R is less than 1 is given by this. Alright, that's the sum of the entire thing. But if R is greater than or equal to 1, the series has no sum. So you can only sum something that is convergent, not divergent. So right here it says when an infinite series is divergent, the series has no sum because the value of R of n, absolute value, will increase infinitely as n increases. It just keeps getting, here's an example, bigger and bigger and bigger, and there's no way to add it up. Alright, so the table on the right shows the partial sums for the divergent series 4, 16, 64, and so on. As n increases, S of n rapidly increases without a limit. Alright, so you can only sum a convergent series, not a divergent series, so R has to be less than 1. So find the sum if it exists. Determine whether each infinite geometric series is convergent or divergent. So again, it's all about R. So to find R, I do the second thing divided by the first thing. When you do fraction by fraction, I'm going to write this the normal way. Divided by 2 over 3. We change division to multiplication by flipping the second fraction times 3 over 2. Hopefully you know that 6 divided 2 is 3. And then 3 divided 15 is 1 over 5. So that's going to be 3/5. Alright, because R is 3/5, that's less than 1. r less than 1 is convergent. So now let's find the sum. The sum is going to be, let's see, S of n equals a sub 1 over 1 minus r. So that means S of n, the infinite thing. I'll do that one. A sub 1 was the fraction 2/3 over 1 minus 3/5. We could combine terms to everything or just put it in the calculator. I'll just be lazy and put it in the calculator. We get the answer 5/3. Alright, so if you add all those fractions up, you'll eventually get to 5/3. Alright, for this bottom one, we're going to try the same thing. Let's see what r is. Second number divided by first number. That does reduce. That turns into, divided by 3/3, that's 3/2. That's more than 1. Because r equals 3/2. That is, r is greater than 1. That means divergent. So no sum exists. Because it keeps getting bigger, too big. We can't add it all up. Alright, what's next? So sigma notation can also be used to represent infinite series. The sequence goes to infinity. Consider then. So the infinity symbol is placed above the sigma sign, the e, to indicate that the series is infinite. So we're going to do the same thing here. So first we got to find the, oh, there's r. R is 4/5. That's less than 1. That is convergent. That's good. We could find the sum. We need to find, next we have to find a sub 1, the first term. Well, that means plug in this bottom number k. Let's figure that out. So 18 times 4/5 to the 1 minus 1. Well, that's 18 times 4 to the 5th to the 0 power. Anything to the 0 power is 1. 18 times 1 is 18. Alright, so now we know a sub 1. A sub 1 is 18. I can now fill in the formula. So the sum of infinite geometric series, if it is convergent, not a sub n, S of n, is that formula a1 over 1 minus r. So I'm going to fill it in. So the sum of the infinite series, a sub 1 is 18 over 1 minus 4/5. Let's actually do this one. So I skipped these are the last one. So that's 18 over 5/5. 1 minus 4/5 is 1/5. So that turns into this. 18 divided by 1/5. I'm going to make that 18 over 1 times 5/1. And that gives us 90. So 90 is the sum of the infinite series. Alright, last example, repeating decimals. So repeating decimal is the sum of infinite geometric series. For instance, 0.45 repeating is 0.454545, or 0.45 plus 0.0045 plus 0.000045, and so on. The formula for sum of infinite series can be used to convert decimals into fractions if you don't know how to do it. So convert 0.63 repeating into a fraction. So there's two methods to do this. There's a formula we're about to use. So I call this method 1. That's this. We're going to write 0.63 repeating is 0.63 plus 0.0063 plus so on. Alright, where I just add 2 zeros. So this fixes to this. This is really 63 over 100 plus 63 over 7 of zeros, 2 zeros, 2 more zeros, over 10,000 plus so on. If you notice, there's an R value. The R value is going to be times 1 over 100. So we can then use our summation formula. S equals A1 over 1 minus R. So then I can say that is A sub 1, our first term is 63 over 100. All over 1 minus R is 1 over 100. Alright, and this is actually pretty simple. If I do combine like terms. That's 63 over 100 over 100 over 100 minus 1 over 100 is 99 over 100. So this turns into 63 over 100 divided by 99 over 100, which I can fix to multiplication. So that's going to be 63 over 100 times 100 over 99. This cancels out. So let me do this. 63 over 99, that does reduce. I divide top and bottom by 3. I get, let's use blue, 21 over 33. That reduces some more. So 7 over 11. And we can check that in the calculator. It's kind of cool thing. So if I type in 7 over 11, I get 0.63 repeating. All right, that's method 1. Method 2 uses some nifty algebra tricks. Let's do that. Method 2, as your choice, either one you want. Uses just straight up algebra. So we're going to say let x equal 0.63 repeating. All right, if we do this, we're going to rewrite it to say x equals 0.636363 and so on. Just keeps running it out. We're going to multiply both sides of 100. That's the going on algebra. We do one side to both sides. So 100x equals 63.636363, so on. All right. Then we use the nifty idea of subtracting x from both sides. So if I do 100x minus x equals 63.636363, so on, minus x, but over here I'm going to plug in x. Remember, x was this thing. Or actually, let's use the bottom one. X was this thing. 0.636363, so on. What that does is this left side combines to 99x. This right side, that whole decimal disappears. It's just 63. Now it's a one-step problem. You divide by 99, and you get what I got earlier, but that does reduce. Right? You divide by 3, makes it 21 over 33, but you divide by 3 again, that makes it 7 over 11. All right, so 2 different options to get the decimal value, or fraction. All right, here's a practice problem. Classify each infinite geometric series as convergent or divergent. Remember, it depends on R. Then if it is convergent, find the sum. And the answer's on the right. All right, thanks for watching. See you in class. Bye.